In electrical engineering and mechanical engineering, there is the notion of operating point. And that's the typical set of values, currents, voltages, forces, positions, velocities, at which a system is expected to be operating. A good example of this is a transistor amplifier. The idea behind a transistor amplifier is that a small change on the input leads to a large change on the output. And preferably that change is proportional. So if there is a change x on the input, then there is a change x times c on the output, where c is a constant. The system is linear. But there is a problem because a transistor is in itself a very nonlinear component. Depending on the current that runs through the base, the relationship between the voltage on the base and the voltage between the current, the collector and the emitter changes. And that relationship, furthermore, is not linear in itself. Now, every electrical engineer knows the solution to this problem. Because if you keep the changes very small, and if you keep the current through the base constant, then the transistor acts roughly as a linear component. In other words, around the operating point Q, if you can make sure that there is only small changes compared to that operating point, around the operating point Q, the transistor behaves linearly. What happens next is that electrical engineers design a whole circuit around the transistor in order to make sure that the voltages and currents are as they would like them to be, are around the operating point. So while the transistor itself is a nonlinear component, the engineers put it into a circuit in such a way that it becomes a linear component as a whole. In a different situation, in computer science, where we want logical switching for the transistors, we actually want to use that nonlinearity. We want to have either a 0 on the input or a clear 1 on the input, and then we design these circuits with the transistors in such a way that these linear operating points are actually avoided. The moral of this story is that an engineer not only uses a model to create a certain behavior in the world, the situation is actually more extreme. Where you could say that a physicist tries to make the model fit whatever he or she sees in the world as accurately as possible, an engineer tries to make the world fit the ideas captured in the model as precisely as possible. The same is true for performance analysis. Within the IRIS research group, I am a member of the predictable performance pillar. Our research focuses on how to make performance of networked systems analyzable. Sometimes we do this by figuring out new ways to calculate the performance of our models, but sometimes we also do this by trying to figure out ways to implement models in the real world for which we already know how to make computations, performance computations. A good example of this, which is important for this course, is the work of Kees van Berkel. He's an advocate of the data flow programming paradigm, which he currently uses to structure petabyte computations that are necessary for handling telescope data in radio astronomy. The data flow programming paradigm forces users to think of data processing as synchronized processing of tokens taken from separate input buffers. When drawing processes as nodes in a graph and buffers as arrows between nodes, we obtain a formalism that has very nice properties when it comes to worst-case performance analysis. The behavior becomes, in a way, linear. Not in the sense of transistor amplifiers, but in the sense of max-plus algebra, which we will learn about in this module. There are a lot of more types of linearity than just addition and multiplication, as you will find out. And one of them is very suitable when you are interested in performance evaluations. So while you're going through the videos in this module, remember that the world does not always need to immediately fit the models that you have in mind. You can also try to build things in such a way that they fit the model that you had in mind, that you were able to calculate. You don't always have to adapt your calculations, you can also adapt your design. And that is called model-based engineering.